Although the morning class was very good at asking questions and getting lots of clarity on things they didn't understand. So I might leave their lesson there. Once you have that, we are going to be going to page 49. No, not page 49, page 57. 1.7b. Okay. We're going to watch a little video. I'll chit chat while we do it. And hopefully by the end of today's lesson, you will feel better about spectrophotometry. You may feel worse before you feel better, but keep asking questions and hopefully we will get there. All right. Do you guys remember which end of the visible light spectrum has the longest wavelength? Is it the red end or the purple end that has the longest wavelength? Red end has the longest wavelength. What could you say about the frequency of red compared with the other visible frequencies? The frequency is low. You see the peak of that wave less often. And you can see here, visible runs from about 400 to 700. You should probably kind of know those end numbers. You don't need to know exactly where each one falls. If you need any information like that, it will be given to you in any questions. But you should know that it's about 400 to 700. Those are not too hard to remember. We will not be doing any of those things except for visible light, okay? Because we're just a high school. And even first year university, you won't do anything other than, you know, your most basic sort of visible light kind of stuff. So if you look on your workbook, unfortunately it is not in color, but you can see the incident light has Roy G. Biv. It is all the colors, but the absorbed light just under the ruby is just Oi G. Biv. Okay, so it absorbs everything except for red, and then the transmitted light is red. Okay, so if you see a particular color, the color opposite is being absorbed. So in that ruby, which is red, what is the main color that is being absorbed? Green. Yeah? And if I said, oh, we've got this solution, like that copper 2, I don't know if you guys remember that from last year. Copper 2 is that beautiful blue color. What light is it absorbing? Mainly orange. Okay, so you might be asked, based on, say they give you some copper 2 and they're like, oh, it's blue. What color will it absorb? If you can just very quickly draw a red, orange, yellow, green, blue, violet, okay, and it doesn't matter whether you go clockwise or counterclockwise, and you can start anywhere you want, red, orange, yellow, green, blue, violet, then you can say, I have an orange substance it must be absorbing blue light. Okay, so it's just a really quick little mnemonic device to help you remember which one absorbs. Okay. There's a little issue in here because this says 450 to 480, and then that one says 450 to 560. I think he just had a typo. I can't do anything about it because it's his video. So there we are. Let's just not worry about it too much. You will always be given any wavelengths that you need in a question. Okay. Okay, so we're just going to take a little look at that diagram in our workbook for a second here. Okay, please work. No, not going to. There we go. Okay. So right now we've shone the light through the prism. It has split into a rainbow. And in this particular case, we are selecting yellow light. Yeah, because that is where there's a little slit here. The light goes through the little slit. Now, if you did not want it to be yellow light, you could move the slit. So instead of being like that, you could maybe have it so that the slit was right here. Yes. So instead you would have like this, right? And then that would allow for green light. I didn't pick green. That was silly. That would allow for green light to shine through if you had the slit at a different place. Does that make sense? Okay. The other way you can do it is that you can either tilt the prism up or tilt it down, so that basically instead of aiming at the slit like this, you'd be aiming at the slit like this, and a different wavelength of light would go through. Does that make sense? And you control that by just turning the little knob that says, literally, wavelength. All right, come back here. Where'd you go? There you are. Okay, cool. So you can see the light here is darker. Here it is a lighter color because there's not as many photons. Some of those photons have been absorbed. So this detector here basically measures how many photons are hitting it. So if you had, if your sample had no colored species in it at all the photons would make it through the solution, and you would get 100% transmittance or 0% or zero absorbance. If, on the other hand, you had 50% of the light getting through, you would have 50% transmittance, and then you would have whatever the absorbance is for 50%. Okay? Do you remember the relationship between transmittance and absorbance? What is it? Absorbance is the? What function would you use on your calculator? If you were given transmittance, how would you find absorbance? You would take the negative of the log of the transmittance. Okay? Yeah. You're not going to have to do that on the AP exam. Pretty sure. Pretty sure. Because they don't give you the formula, so I don't think they're going to care. So this is really important when it comes to reaction rates, because we can use a spectrophotometer to measure rates when we have a colored substance. But if your reaction doesn't involve anything that has a color, can you use a spectrophotometer to measure the rate? No. But this is a really nice way to measure things, because let's say you have reactant A, reactant B, and you pour them together, okay? And maybe reactant A is purple, okay? Pour them together, and the purple color starts to get lighter and lighter and lighter. Why? Because purple stuff is getting used up. Yeah, purple stuff is getting used up, so it gets lighter and lighter and lighter. If, when you pour them into the little container, and I'll show you the little container right now, and we don't touch these with our fingers because it's important that the glass remain really nice and not greasy. No fingy prints. Okay, that's called a cuvette. It looks just like a test tube. The only thing that's different about it is that it is a very, very clear glass. Okay, so there's no imperfections in it like you'll have in just a regular test tube. It's just a much nicer one. They're almost always 1 centimeter across to make the math really easy, because that means your path length is 1, right? Which makes math, anytime you have a 1 in your math, that makes life easy. So we poured in our 2 reactants. One of them was purple. This is now getting lighter and lighter and lighter. But before it finishes reacting, as soon as possible, what I'm going to do is I'm going to pop it into our little machine here, right? And I'll have selected my wavelength appropriately, which we'll talk about in a moment. And I'm going to watch the absorbance go down and down and down. And so I can measure the absorbance at 0 seconds, 5 seconds, 10 seconds, 20 seconds. And this is because the machine just keeps spitting out numbers at me, it's a really easy way to measure a rate. So if you have the choice of using a spectrophotometer to measure rate, it's a really good one. But if you don't have a colored species, so sorry, you cannot do it. Alrighty. And we're just going to pause right there, because we are going to talk about the ideal wavelength. Okay, so we have this ideal wavelength at which the sample absorbs color. And that is going to be the wavelength at which the absorbance is the greatest. This is on page 858. Okay. We call this the lambda max. Lambda max. I'm not sure I spelled that right. I'm not sure if there's a B in lambda. I think it might just be LAMDA, but anyway. And we can find this lambda max by plotting an absorbance spectrum. And the reason it's called lambda max because it is the wavelength at which absorbance is the greatest, maximum. Okay. So if we look at this graph coming up here, we're not going to watch the video. If you want to go back and watch the video later, here is a graph. Point to your partner or someone near you and show them, and if you don't have anyone, you can just point for yourself, where is our lambda max? Where is our ideal wavelength for this particular substance? hopefully you just chose the highest peak, okay? So you simply choose the wavelength where the absorbance is the greatest. So on our y-axis, we have absorbance, and on the x-axis, we have lambda max. And so what we would do in order to make this plot is we would take our substance, okay? We wouldn't do anything where we have a reaction going on. This would just be like a sample of the purple substance at a known concentration, okay? And we put it in here, and we measure it at, say, 400 nanometers. And the absorbance comes up, and we get a dot on our graph, right? And then we measure it at, I don't know, so let's say this is 500 nanometers, or let's say we measure it at 450, and we get a dot. And we measure it at 500, and we get a dot. And we measure it at a whole bunch of different wavelengths, all the same sample. Okay, why will you not shrink for me? I hate you. Ugh. Computers, they sometimes just start doing things differently, and I don't know why. Can I make it go smaller? No. Do I have a view? Zoom. Ah, zoom out. Okay, that's awkward, but it works. This is one single sample. Single sample measured at different wavelengths. So this is what we would do in part 1 of the experiment. What we're doing is we're finding the ideal wavelength, the lambda max. So that's part 1. Before you do anything, unless you've done this before, you need to find your ideal wavelength. And then for the rest of the experiment, whatever part 2 is, you can have different part 2s. Sometimes you'll be finding a concentration of an unknown. Sometimes you'll be measuring a reaction rate. Part 2 is going to use only the lambda max. It'll only use the ideal wavelength, okay? And we'll talk about those part 2s in just a bit. Now, just because we can, we're going to look at the relationship between absorbance and transmittance. And I feel like actually the picture on the next page is better because it shows that the absorbance and the percent transmittance, they're actually mirror images of one another. As the absorbance goes up, the transmittance goes down. As the transmittance goes up, the absorbance goes down. And so the lambda max, if you're measuring absorbance, is actually the lambda min for the transmittance. But nobody ever measures transmittance, so you wouldn't really do it. Okay. All right, and then there's some questions. Pages 61 to 62 are going to be homework. Let me just write that up here. 1.7b, pages 61 to 62. There's also going to be 1.7c. and there's like some videos to watch, and there's a little activity to do, because this thing takes 15 minutes just to warm up so you can use it. And there's only one of them. It's not really useful for all of you as a class to be doing. I did try it one year, and I had people like booking in after school times. I hated every minute of it. I was like stuck here till 5 o'clock, and it was just bad. So instead of that, 1.7c, which is going to be the second part of your homework, there is a video showing an actual spectrophotometer. You've seen the little diagram, but it actually like shows an animation of how it works. And then there is a little simulated activity which allows you to grab a cuvette and put it in the pretend spectrophotometer and do some measurements and record some things, and it lets you do all that. So you're going to be doing that for homework as well. So that's 1.7c. If you don't have time to do the entire activity, or if you feel like you need a review, at the end of 1.7c, there are a couple of videos that just kind of walk you through the process without you doing it. You can just watch them, okay? So like I said, if you need a review of it, or if you didn't have time to do the activity, you can just watch those. But we are going to move on to 1.7d. Or actually before that, we did something in the other block that I forgot to cover. So let's talk about that. And this would be, and if you need some paper to write on, you can grab yourself a piece of paper from the back. This is a possible part 2. To the experiment. Remind your partner, what was part 1? What did we do in part 1 of any spectrophotometry kind of lab experience? We find the lambda max. And what will you be changing in this part 1? You will be changing wavelength. And what do you plot? Absorbance versus wavelength. Okay, so that's part 1. A possible part 2, and this is relating this to your current unit, a reaction rates kind of a thing. Let's say we've got our purple substance and we have discovered its lambda max. Does anyone want to choose a value for our purple substance that, like, what color light would we be looking at? Having go through the machine, if we have a purple substance, we would be looking at yellow. So we're going to, actually, you know what? We're not going to do purple. We're going to do blue, because I have a blue pen on my screen and I don't have a purple pen easily accessible. Okay, so we're going to do blue, so it's going to absorb orange light. Okay, so part 2. We're going to have a reactant here that has blue substance. And we're going to have reactant B, which is colorless. And we're going to mix them together They are mixed in a cuvette. Okay, which is like that little test tube thing. Can I not go any further down on this? Oh my God. Okay. Why? Oh, I can. See, sometimes it'll let my finger move the screen, and sometimes it'll make it draw with my finger, and I don't know why. I gotta go talk to Mr. H. He'll probably know. Okay, so we've got them mixed in a cuvette. And what's gonna happen, and now they will start to react. So we're gonna have time 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I got 10 little dots in there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 little dots. And maybe at time equals 5 minutes, I have 1, 2, 3, 4, 5 little dots. Why did I not? Oh, I'm going to make it 12. 12, because that's divisible by 2, divisible by 2, divisible by 2. That makes it better. 1, 2, 3, 4, 5, 6. And then at t equals 10 minutes, I'm going to have 1, 2, 3 little dots. So you can see the blue reactant is decreasing over time. Our absorbance, let's just say that we get an absorbance of 1,000 here. What would the absorbance be after 5 minutes? Over here I have 12 little blue things. Here I have 6 little blue things. Over here I have 3 little blue things. What would my absorbance be at 5 minutes? It would be 500, okay? And how about at time equals 10 minutes? It would be 250, okay? Now, this experiment, we have done this at our lambda max. And if you remember our lambda max, here is our absorbance, here is our lambda value. I'm only going to have one peak in this thing just to make life easy. Okay, so it's going to go. Okay. Why do we choose the one where the absorbance, the wavelength where the absorbance is the highest? Why don't we choose a different lambda? A different wavelength? Yeah. Yeah, you can have a greater range of data. Okay. So if I was to do it at the different lambda max, my absorbance might be I might have 10 and then 5 and then 2.5, which is still measurable. But then let's say I did it at a third one. I don't know, green. There we go, green. Oh, that shouldn't be lambda max. That should just be a different lambda, because it's not the maximum wavelength. It's just some other wavelength. perhaps when I have it way over there, my absorbance just shows 0 and 0 and 0. And do you see how that becomes kind of useless? Right? And over time, this one, after 10 minutes, I get 250. If I went to, say, 20 minutes, I would be down to half of 125, which is what, 63.5 or something like that, 62.5. But if I had this one, this would be 0.625, and that's getting too small to measure, right? And then this one would be 0. So we want that highest absorbance wavelength so that our data can be the most meaningful. Does anybody have any questions about any of this? Okay. If you want to hear or like a really amazing discussion, I think it's because also I did not do as good a job explaining it in first block. So there was a lot of confusion because they were like, what's happening? We're reacting. What's happening? I did not explain very well. I did a better job here. So yeah. Anyway, what the graph for this would look like if we were to take this one and then plot it over time. So this would be absorbance versus time. And eventually it would go to 0. So you'd end up with something like this. Is good? And what is absorbance telling us about? Absorbance is related to the concentration. Yeah. And you can do, yes. Absorbance doesn't have units. So if you were doing a calculation where you were just like, I don't even want to bother converting my absorbance into concentration by doing a bunch of math, you could do a reaction rate. Like if you were just doing it for comparative purposes, you know, this reaction rate with that reaction rate, you could just do it in absorbance and you would have like no unit over time. Yeah. But most of the time, what you will do is you will find the absorbance that relates to the particular concentration. And then you will use that to convert your absorbances into concentrations. Okay, so there would actually, in that experiment, there would be part 1, find the lambda max. Part 2, find what absorbance goes with what concentration. Okay, and then part 3 would be to do this. Okay, and we're going to now take a look at what absorbance goes with what concentration, and that is called Beer's law. Okay, so we're going to we're going to go on to 1.7D, which is on page 68. So this is relating absorbance to concentration. And again, we have a little video here, so let's take advantage of that. So do you remember last year when we made a solution? How did we do that? If I wanted to make a 0.5 molar solution of a particular volume, what sorts of things would I need to do? Pardon me? I could do a titration if I already had the solution, but what if I wanted to make the solution from scratch? I get not an Erlenmeyer flask, but a this is Erlenmeyer. Okay, this is good for a titration. Do you guys remember what this is called? Volumetric flask. Yes. Okay, that's a volumetric flask. And we use this to make solutions because the neck is very skinny. So a small difference in volume makes a big difference in the height of the liquid. Okay, so you can be very precise. All right. What will we put in here? The solute, whatever it is. Okay. How do I know how much solute to put in? You would need to use the molar mass, and you would need to figure out the volume and the molar. You would need to do, okay, I've got my volume, my molarity, I would find moles, and then I would find grams, and then I would weigh it out, and then I would put it in here. Sounding familiar? Don't worry, we're going to do this again this year, so you get practical hands-on experience. Now, I've got my solute in here. What do I do next? Fill it 2/3 with water. Why do I not fill it all the way to the line? Because I have to mix it, and if I fill it all the way to the line and I do this, nothing really moves because the water's all the way up to here. But if it's only about half or 2/3 full, it can swirl. Then, once it's all dissolved, what do? Water all the way up to the line, and then stopper it, mix it properly. Okay, now we have our solution. Now, this is a 0.5 molar solution. Do you guys remember doing dilution calculations last year? They're like, no, that's okay. We will review dilutions at some point. Believe me that you could figure out how much of this you needed to make a 0.4 molar solution or a 0.3 molar or whatever. Or perhaps rather than making 0.5, maybe you made a 1 molar solution and you're going to use that and you will dilute it down to 0.5, 0.4, 0.3, 0.2, 0.1. So you have little solutions of each different concentration that you know are specifically correct. Okay, so you've got these. And you're going to put them in one at a time. You've already done part 1 of the experiment. You've figured out your lambda max for this thing. Yes? And so you put it in. You put in your 0.5, and it gives you an absorbance, and then you take it out. And then you put in your 0.4, and it gives an absorbance, and then you take it out. All right, but we're going to watch a little bit more of this and get there. Anyone want to take a guess as to what the molarity is of this unknown? Sorry? 0.35, because it's kind of in between the 0.3 and the 0.4. Okay, it's hard to tell. Maybe you think it's 0.3, maybe you think it's 0.4. Hard to tell, which is why we don't rely on looking at the color to figure out our concentration. Okay, not unless we really don't care about how specific we are. unless you have nothing in the cuvette, in which case nothing gets absorbed. Yeah? Although, to be honest with you, all the ones you're going to run across, they're all going to have a path length of 1 centimeter. Okay? Like, I have yet to come across a spectrophotometer in like undergraduate science where the path length was not 1 centimeter. Okay? Presumably there are others in other places, but it makes your math really easy because it is 1. This formula here, if you're worried about remembering it, you don't need to, because guess what? It is in your AP chemistry equations, that blue package that you got of stuff, and down at the bottom here it says A equals epsilon BC. Now instead of L for the path length, they use B. Okay, but you don't have to remember that, because over on the right-hand side, it tells you that A stands for absorbance, epsilon stands for the molar absorptivity, B is the path length, and C is the concentration. Mostly all you'd be able need to do in this is just plug some values in and get your answer out. Okay, so it's pretty straightforward. Mm-hmm. What color should that wavelength be? Should be green. Okay, green is opposite red.
Please excuse the interruption. In a couple of minutes, we're going to be starting our first flex period of the school year. So a few reminders, as we've got a different model than we've had in previous years. Flex will occur on Tuesdays and Thursdays for 30 minutes between period 3 and 4. The intention of flex is for self-directed study and activity for students. That means for students in grade 9 through 12, you're expected to be in a classroom, in the gym, in the library, or in the commons, working with classmates, getting help from teachers, completing homework, or any other focused learning activity. Students aren't to be gathering in hallways or bathrooms. as we don't want to be disrupting learning that's going on in classrooms. For grade 8 students, for the month of September, grade 8s are in scheduled assigned flex classes. The assigned class shows up on your timetable. If you don't have your timetable, the lists are also posted in the library. So again, grade 8s go to their assigned flex for the first six flex sessions of the school year. And then we'll have choice starting in October. Okay, we look forward to everybody making good use of this time. Again, a reminder, it is instructional.
I hope that got recorded.
To be on their phone during class time, unless using them for academic activities. Thank you.
Oh my God, I need to hang up this phone quickly. Okay. All right, I think we got about 1 minute left because that clock is a little bit slow. Just so you know, what you would do is you would take your unknown, right? Let's just jump ahead. There's our unknown. There's our absorbance. And you can just read off the graph. You can say, here's my unknown absorbance at 0.47. You can read across and then read down and get the concentration. Or if you want to be even more precise with it, you can use your y equals mx plus b and plug in 0.47 for the y value and solve for x. Yes? And I think that's as far as I got with my other class. So your homework is 1.7b, pages 61 to 62, and 1.7c. And you probably actually do have a minute or so before the bell goes, but just in case. Yes?
You'll get an absorbance of 0 on the filter if there's nothing in the bag. But you also get a 0 if the shine has red light or red solution.
I don't know. That's a really good question. I'll have to look that up.
Yeah, the red solution normal red light and you absorb all the other colors. You have the red light. You're right on. Theoretically,
Yeah, I honestly don't know. I'm going to have to go ask a physicist. I feel though, like, even when I said, even if you had a cuvette with nothing in it, the cuvette itself will absorb a little bit of light, which is probably why the B value is not 0. Does that make sense? And if you have, even if you just have water, that's one of the reasons why, and we didn't talk about this, before you start any experiment, you actually put a blank in and set that to 0 so that that takes care of your cuvette and your solvent, right? So anything that's in there, cuvette, solvent, anything that absorbs at that wavelength will be zeroed out because you'll set the machine to 0.
are molecules in the solution going to absorb some of the light?
Yeah, there's going to be various ones that absorb like little bits of light, but not very much. So yeah.
Shine of light. If you shine, let's say you have an atom that has electrons